folks. Today we're going to be covering section 2.1. Here's a quick view of the schedule that I have posted. This video is specifically for Tuesday, May 17th, so per the schedule we'll be covering section 2.1. What I like to do ordinarily is I make PDFs available for the students to print. Right? You don't have to print these, of course, but if you do, I purposely made it in color to sort of emphasize details of it. And if you do print it, you can annotate if you find anything useful. Anyhow, this is more or less an overview of the formulas that you would need for section 2.1, some reminders and things. All right. In addition, I have a predefined coordinate plane, a blank, right, so the axes are already drawn. I would, if you're following along by hand, maybe print about 4 of these, all right, because there's that many problems I'm going to use to illustrate. Okay, so just 2 handouts today. As you can see behind me, here's a little diagram that I prepared ahead of time, and I want to add to. I think it's getting a little dark, so maybe what I'll do is I'll turn the light on first. And fill in some information here. All right. The actual name of the section is the rectangular coordinate system, which is one of at least 3. All right. You're only responsible for this system, which is why I put it in red per se. Just kind of draw emphasis. But these other things exist, and they are interesting, and there's some symmetry there. So maybe it takes maybe we should take a moment to just give some tidbits about that. Anyhow, of the rectangular system, otherwise known as the Cartesian system, for René Descartes, there's a 2-dimensional system, which is where we're starting, right? And there's a 3-dimensional system, which is something you're more likely to see in actual calculus class. All right, same thing with polar and spherical coordinates, depending upon where you're going, where you're taking your classes. All right. Anyhow, as you probably know, the ordered pairs that exist in a 2-dimensional, i.e. mathematically flat coordinate plane, are designated by an x value first and a y value first. Okay, so remember, when you're plotting dots, just as you probably already know, this is always first, this is always second. Right? In theory, when you get to 3 dimensions, which is again either in a calculus class usually or maybe a physics class, there's the added dimension of z, so this would be x, y, z. That's a little bit trickier to do by hand, which is why they usually implement software like Maple or Mathematica. Anyhow, you're not responsible for that. You're just going to be dealing with Cartesian 2-dimensional systems of x and y. All right. These other things, just to again cover some bases here. This is also 2-dimensional, and the coordinates would be a radius instead and an angle. All right, known as theta in this case. Sorry for the glare. That's the actual projection of my camera that you're seeing right there. This is known as theta to represent the angle. Right? In spherical coordinates, it would be 3D. That sphere is all 3D, of course. Right? And there would be, like before, an extra coordinate. So the extra angle would be radius, theta, angle, and then phi. All right? Another Greek letter to add to the list. All right. Anyhow, again, you're only responsible for what you see in red here. All right. We're going to be dealing with things that are mathematically flat, so they're truly abstract. They're just drawings. All right. Otherwise known as the rectangular system, right? X's and Y's. Okay. And having said that, let me pull up my coordinate plane just to remind you of some terminology, as it's useful, I think. Oh, I put some lapel on. Sorry. Give it a minute to load here. I'll erase some of this. There's another thing. Adobe forgot to plug it in. It's the end of the day, folks. Can you tell? Voila. There we are. So here we have it. Let me get rid of the gobbledygook here. Here's our coordinate plane projected. Prepared and projected. You, again, not to insult your intelligence, may know by the time you're in pre-calc what the names of everything are. But, erring on the side of caution, let's fix some, right some wrongs here in case. All right, this firstly is the x-axis, which is usually just abbreviated x, all right? And the vertical axis is the y-axis. And then, because this comes from the Middle Ages, the late Middle Ages, there are some Roman numerals that are used still on this to not refer to or not confuse with an actual point, but just designate one of the quarters of the picture. This is quadrant 1, capital I, right? And everything is right counterclockwise, so anything over here would be in quadrant 2, and this would be in quadrant 3, and this would be in quadrant 4, IV. Right. Mark is getting bad here. Put that one aside. Okay. Now remember, where the axes cross is famously the origin, and it has the ordered pair 0, 0. Right? Anything that is to the right side of the origin is a positive x, and anything to the left side of the origin is a negative x. Right? Similarly, anything up from the origin would be positive y, anything down from the origin would be negative y. Right? In a nutshell, right? Anything in quadrant 1, it would be a point that is x at first and then a y, right, would be a positive and a positive. Right? And over here in quadrant 2, it would be a negative x and then a positive y. Right? And in quadrant 3, both negatives. And in quadrant 4, a positive x and a negative y. Right? Remember, you have to resist the temptation when you're doing this by hand to actually leave a mark until after you've gone the second number, whatever the amount is, right? So just remember, right, x is always first, y is always second, all right, before you make a dot. Okay. I think that's good. All right, now if you turn your focus to this diagram that I have made today, let me explain some details here. Again, this is an overview, more or less, of the formulas that you would need in section 2.1. Okay. Now, it starts basically with the good old Pythagorean theorem, right? Which is, think about it, the gift that keeps on giving, because the things that follow are really derivatives of that, right? You'll see why in a moment, right? A couple of things to remember. First of all, the Pythagorean theorem, famously a squared plus b squared equals c squared, all right, is for use in when you have right triangles, all right? So here's an example of a right triangle, all right? And there are these labels which a person should know, all right? Because if you have to input anything, you don't want to inadvertently put something in the wrong place. All right, I like to label it this way. All right, I put the B more or less in the label along the bottom. All right, because that seems reasonable to me. B bottom. All right, and therefore I will label this side here A. All right, just to make some kind of logic of it. B is in bottom, A is in altitude. You know, that's a bit of a stretch, but it works. All right. Anyhow, they are each known as legs, right? And for that reason, since they're basically the same thing, they're interchangeable in the formula. So if you had a number here or you had a number there, you could put them either one, whichever your preference, in A or B, right? The one thing that is non-negotiable, all right, is the actual C value, all right, which is known as the hypotenuse, all right? The hypotenuse is the fancy way of saying the longest side of the three sides of a right triangle, all right? If you need to identify it without it being specified verbally, it's always directly across from the box, right? So if there is in fact a number here across from the 90-degree angle symbol, right, then you have the hypotenuse and it must go in place of C, right? If you don't have it, just leave the letter, right? These are interchangeable, this is non-negotiable, right? Anyhow, you could identify the legs usually because the box would in fact be written in the corner there, so they're always perpendicular, right? There's always a 90-degree angle separating the legs, right? What I added to this, because it's going to be relevant to us later, is that let's just say that the end points of the corners here of this triangle, the end points of the hypotenuse, if it was superimposed upon a coordinate plane, it would have ordered pairs. It would have coordinates x and y. Now what you see here is that there would be two in this case, so to sort of differentiate one from the other, to distinguish one from the other, I put little subscripts. Right? Do remember that subscripts are not an operation, they're more or less labels. They're just to say that there's two of these x's and there's two of these y's. Okay. Now, I'll get back to this other side. From the Pythagorean theorem, right, we have something known as the distance formula. If you've taken a physics class, very likely this had come up in a physics class, even if the labeling is slightly different. All that has happened, if you examine this, is that somebody went through some algebraic process to get from here to there. Right? You'll notice that in the case of the Pythagorean theorem, there is no square root. But in the distance formula, there is. A very long one here. How would that even be accomplished? Well, someone would be solving for the value, in this case for a hypotenuse, and in this case for a distance. All right? But in order to arrive at the distance, you need the ordered pairs of 2 points in order to insert them here and here and here and here, respectively. All right? So rather than have a nice rock solid figure to represent a leg and then a second leg, a side and a side, you have just merely the endpoints to implement. All right? Anyhow, if you were to take the square root of c squared, that would eliminate essentially, as an opposite operation, would induce a cancellation effect. And in order to get away with that, to solve for c, even if you change the label, you would be obligated, your hands are tied, you really must do that to the entire other side, hence the square root. All right? And again, instead of having a single solitary number, you have the difference of two x's. Right? Instead of this single solitary number, you have the difference of two y's. Right? Everything else is essentially the same. All right? The labels have been changed to protect the innocent. Right? So again, instead of C, it's called D because that's intuitive to the phrase distance. Right? D for distance. All right? That's going to unfortunately come back to bite us because when we start talking about radii and diameters, you don't want to confuse D with being either, with being a diameter per se. Right? You got to be a little extra careful. Anyhow, distance formula is derived from Pythagorean theorem. That's what's important. And if you take the logic a little bit further, here's what you'll see. There's the actual equation of a circle. Right? The equation of a circle is basically the distance formula with certain specific labels changed, right? Because they're important. They more or less have a job that we need them to perform for us, right? I put this in color again to emphasize some points. If the purpose of the distance formula is to calculate the total distance between 2 points, then the equation of a circle is basically to identify the radius and what would be the center of the circle. All right? I purposely put a comma here, all right? And I made these in matching colors, red and blue, because I wanted you to think of this, even though it's labeled H, it's just the unique labeling of our textbook, as being a type of X. right? And K as being a type of Y, right? I know that that's a little confusing, of course, but if this is an ordered pair, the center of the circle, X comma Y, just to differentiate, to distinguish it from what has to be sort of frozen in place in the formula, you want these things to remain, you're not substituting that particular X or that particular Y. All right, we've given labels to this X and that Y, right, H and K for whatever reason. All right, anyhow, the distance label has been changed to R, all right, as in a radius, because we're talking about circles also. So this is more or less the same. There's a difference here, and then it's squared. And this is more or less the same. This is a difference here, and it's also squared. And they're all underneath the radical. But the labels have been changed to R, H, and K, right? That is the center of the circle. That is how wide the radius is. All right. Then there's one step further, right? There's some all wise purple eyes here. All knowing, all seeing, right? The look of the standard form of the equation of a circle is to have it arranged this way. And as you can see, what has happened? Well, it's sometimes impractical to have a radical. All right? If you had your choice between having a radical and not having a radical, this is the option. Right? So remember, if you square this essentially cancels that. Opposite operations induce a cancellation effect. And in order to get away with it legally, if you've done it here to this side of equals, you're obligated. Your hands are tied. You have to do it here. So that is why it is R squared. And then the guts here of the radical, the radicand, is written here. Right? Often in the homework, they'll ask you, oh, find the equation of a circle, but don't stop there. Write it in standard form. Okay? That gets a little tricky again. You got to be careful with the labels in terms of what you're actually using for a R value. Right? You don't want to inadvertently use the wrong R value, right? If you're dealing with a diameter per se. Right? Now let me go back up the page because I got to remind you of something else. Let me complete this thought. I appropriately place this thought balloon here because I want you to beware. Right? If you have the equation given to you and they say, well, what's the center of the circle? All right. The signs of what would be the center of the circle, again, this is essentially an X and this is essentially a Y, all right, are counterintuitive. So if you see a negative here, just understand that it represents a positive, all right? If you see a negative here in the formula, again, that represents a positive, right? This hasn't changed, right? It screws up a person the first time that they see it because they're like, oh, I see a minus, so they automatically think it's a negative coordinate, but it's not, okay? It's counterintuitive. Be careful of that, okay? Another thing to think of, sometimes the distance is a hypotenuse, and simultaneously, coincidentally, it is also a diameter, right? It depends on the circumstances of the problem. You have to be careful, all right? The last thing before I get to some problems is the other side of this page here, right? There's something known as the midpoint formula, right? What is its purpose? Essentially, it's the location, determines the location of halfway between 2 points. Now, if it happens to be the 2 points happen to be the endpoints of a diameter, all right, then the midpoint would be the center of a circle, just coincidentally, right? So remember, the midpoint of a diameter is also the center of a circle, if you happen to be looking for it, okay? What does the formula look like? It's remarkably similar to these other things. I put this dashed sort of line here because I don't want you to confuse the thing that is immediately underneath it with what I'm talking about here, all right? These are different formulae, all right? Midpoint, abbreviated MP, military police, right, is a location. So it is an ordered pair, all right? Basically, you're taking an average of your X's and an average of your Y's, all right? So since there's 2 here and 2 there, you divide by 2, right, to get halfway of each, right? Halfway of the X's, halfway of the Y's. All right, separate them by a comma. And notice that you don't want to confuse this. Notice the subscript. So these are the 2 things, the 2 unique X values added. Whereas in the distance formula, you're subtracting them and you're specifically putting the second first, right? So do be careful of that. You got to be very careful always with the signs. Right? Right. That's it. All right. So let's get to some problems. All right. And I'll show you how this works. I may need to go back to my graph paper. So I'm going to do that right now. And I'll write the example off to the side to make it as legible as possible. All right. Maybe some light would be good, as long as it's not interfering. Okay. I'm going to put the question up here above the projection. All right. All right. Here's the first example. All right. What I'd like you to do is try to graph and then find the distance. Given these ordered pairs. Right. -3, -1, and 2, 3. Right. That looks like it's visible. All right. These are not labeled, of course, but assume that each one of the boxes, just because it's convenient, are 1 increment each. Right. So if you do this one, -3, -1, you start at the origin, go over 3 spaces, resist the temptation to make a mark until after you've gone the y amount. If it's -1, you go down 1, so you're going to put a dot right there. Okay. And then, you could label it if you'd like. Right. Sometimes that's cool to do that. And then over here, you could do the second point, so go back to the origin and count over +2 is the right direction, so 1, 2. And then up 3, 1, 2, 3, put it up there, and then you have that. Now if I were less of a dodo, I would have gotten a ruler, so I'm going to do that because I want to connect them. So bear with me one moment. I hope I don't get this too dirty. Here's a good level to connect these dots. So I'll use green. All right. The trick to this is that you do it on graph paper, and then you get a good ruler, and you be very anal retentive. Connect the lines like that. Now, this is, for right now, it is simply a distance. It has no other point to it other than that. Right? If you've done it on graph paper, now there is an option that you have technically, which is that you could take advantage of the grid lines and sort of sketch out a right triangle that would connect this as if it were a hypotenuse instead, right? So I'm going to very faintly draw dashed line this way, and then I'm going to connect it perpendicular to this dot this way. Right? And there they have a 90-degree angle. Now, why would you bother doing that? Because if it's on graph paper, and this only works if it does, all right, you can count the boxes. Right? That means that the dimensions of this side is 4, and the dimensions of this side is 1, 2, 3, 4, 5, 6. Pardon me. Is it 6? Did I put that in the wrong place? Yes. No, ding, 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 dong. This is a little bit shorter. So ain't nobody here to help me. Sorry. There's 3. -1. Okay. Little adjustment, sorry. Okay. The dimensions of the boxes, that's 3 increments, and that's still not low enough. I have to get my eyes checked. Seriously, I gotta get my eyes checked. All right. 1, 2, 3, down 1. Sorry. Okay. All right. Put this down. Fix this while you do it. Okay. 2, 3, 3, 1. Okay. All's well in math land? I hope so. All right. Here's my little imaginary triangle, right triangle, to connect these points. Just underneath it, that way, and then connecting it vertically that way at a 90-degree angle. Right? Again, if you do this on graph paper correctly, not like Dodo here, you could take advantage of the boxes by counting the boxes. So it's 4, 1, 2, 3, 4 blocks that way, and then 1, 2, 3, 4, 5, as it should be this way in the x dimension, right? Why do you care? Well, if this is a right triangle because you've made it as such, then that means that this would conform to the conditions of the Pythagorean theorem, which is 4 right triangles, which means you could call this distance a c and then take advantage. Right? You do have to perform a little bit of algebra for the cancellation effect to get it just so, but you would have the dimensions of 4 and 5 respectively. So if you have a 4 here and a 5 here, and c, pardon me, I'll use this in a different color. Your c squared would be 16 plus 25, and then your c squared would be 41. And then to solve the c to get the genuine distance, although it's not immediately satisfying, you would take a square root to cancel what is being squared. And to get away with it, remember the balancing act. You must do it to the opposite side. So this would be the square root of 41. Now, here's a little speech about that. That is the exact answer, which in math world is always preferred, right? It isn't satisfying because we live in, real world where decimals are normally fine as long as they're rounded, right? But an irrational number, as the square root of 41 would prove to be, is actually the perfect answer. It's exact, right? If you were going to round it, right, you might start by estimating if you know your perfect squares by heart, all right? Not to go off on too much of a tangent, but the square root of 41 would be in between the square root of 36 and the square root of 49. So if you had a guess, square root of 36 is exactly 6, because 36 is a perfect square, right? And the square root of 49 is exactly 7. You might guess that this is something in between them, so 6.5, right? If you take your calculator and get the more precise measurement, that is extra decimal places, rather than just 2, right? What you'll see is that it's rounded more to about 6.4. If it makes you feel more comfortable to get the decimal number, all right, as long as it's rounded reasonably so, all right, that's fine, all right? We're not trying to overcomplicate things, but just beware. This is an approximate, all right, and this is the exact answer, square root of 41, which you may, again, you have a fight in your mind, you go like, I don't like that, I like the decimal, but that's actually a better answer, all right? So, it would be difficult to measure correctly by counting boxes. It wouldn't work. A diagonal line, which is why you don't have to do it this way, it's just an alternative. What you could opt for instead is to just use these endpoints, right? Just be very careful about how you insert them in the formula. So I'll do it over here, all right? If you use the formula, and hopefully this is visible. Turn that off for a moment, see if this works. It's kind of faint, the green. The distance formula using ordered pairs would be the derived version of the Pythagorean theorem that allows you to opt for coordinates. So here it would be all its subscript glory. And not to be confusing subscripts with superscripts, right? It's very faint, kind of on purpose. I write things in green a lot of times because then I could draw on top of them. So I'm sorry for that. Anyhow, what you would do is very carefully insert your x's and y's into the formula and follow the correct order of operations, which basically means you must be doing the innermost parentheses before you take a square root. All right? Now, you have a little artistic license as well, all right? It doesn't matter which one of these is the set of x1 and y1. What I would do is the lower left one, I tend to make x1, y1, and the upper right one, I tend to make x2, y2, but that's an option, right? You're gonna get the right answer regardless, just make sure that you are consistent. The 2's go together as a pair, the 1's go together as a pair, all right? That is the subscripts I'm talking about, all right? Now you superimpose them on the formula, all right? So, x2, the way I've decided it, is the number 2, right? So I'll put a 2 here. There happens to be a minus in the formula. You have to be careful of that. The x1 is -3. So I'm going to squeak in -3 here. All right. If I continue just plugging in y2, the way I've decided it is 3. There's a minus in the formula here. And then there's a -1 in the y1. All right. Again, adjust the signs before you follow the order of operations. If you have a double negative, essentially, that there's no number in between these, all right, fix that. All right. Remember, a double negative is a positive, right? So this is essentially 2 plus 3, which means that you end up with 5 squared, right? Not coincidentally, right? As from before. Over here, 3 plus 1 would end up being 4 squared, which again, not coincidentally, as before, right? This is still underneath the radical though, right? So you still have to simplify the guts of the radical, namely the radicand, that's the fancy name for it, right? Which entails not adding first, but squaring first. So you end up with 25 plus 16 nonetheless, and then if you add them, you get 41. That means that, again, the distance, regardless, is the square root of 41, which is about 6.4, all right, increments along this drawing here, okay? More than one way to do it, all right? Now, as a second part to this, and maybe I'll put the light back on. Let's say, using the exact same coordinates, you find the midpoint, right? That would be pretty hard to do even if you were eyeballing it on graph paper. All right, you can count boxes vertically or horizontally. All right, but to count the boxes along a diagonal line, that's not too easy. So here's what we're going to do. All right, we're going to use the midpoint formula, implementing these ordered pairs again, to calculate the midpoint. Okay, the midpoint you could kind of guess is somewhere in here. So if it would be halfway along this green line, you have to figure that it would be somewhere around there, right? What is the exact figure of the x-coordinate and the y-coordinate? I wouldn't really guess, all right? I'd rather use a formula to get it exactly. Right? And again, I'm going to just borrow these ordered pairs in a different formula. So if the midpoint formula is basically an average of x's, and comma, an average of y's, right, I'll just insert them appropriately. Right, so the way I've designated x1 and y, x1 and y1 and x2 and y2, I would put -3 here plus 2, and it's over 2 because again it's an average of the 2. And now as for the y's, I'm going to put a -1 here plus 3 over 2 as well. All right. The way -3 plus 2 ends up, this is a -1. The way -3 plus -1 plus 3 works out is that this is a positive 2. All right. Which means if I were to simplify it, the midpoint would be -1/2, comma, for the x, And then 2 over 2 simplified is just positive 1. Right? You could opt for not putting the positive if you'd like. Let's see if that makes sense according to my guess. All right, if I were to start at the origin here, I should try not to move the projector too much, and go over negative a half, that would be halfway in between here and here, and then up 1, I'm right on the line. So it was a good guess. All right, that's the midpoint, negative a half, comma 1. Okay. All right, again, try to guesstimate by eyeballing it. It's not impossible, but it would not be, the formula would give you an exact answer, so you would opt for that. Now, let us say hypothetically that you were asked to find the equation of the equation of a circle, but I got to draw a little bit. So let me get the gobbledygook out of the way. All right. Using these same points. Let's do this. If distance d equals the square root of 41 is coincidentally a diameter. Right. Let's try to write the equation of circle in standard form. Right. What that means, and I wish I had a better stencil than what I'm going to use. If this is a diameter, there would be a circle around these 2 points. It would be on the edge of it. Let me see if I can get something to draw that nicely. I'd rather not use my pots and pans if I can help it, but I may have to. Let's see if this works. Never thought I'd be grateful for being home, but too much. All right, I'm gonna do it by hand, which is gonna be sloppy. Unless I can get a large protractor. Just a side note, if you're doing this by hand on graph paper, that would be smaller than my projection, of course. Do yourself a favor, get a nice compass, all right? The metal type that is adjustable from the center, all right? This is a Statler, I believe. Yes. To do any sort of drawing of circles, all right? I know that they sell, usually as part of a kit, a protractor and a compass in, at the grocery store. They're always crappy, all right? Do yourself a favor, spare yourself the aggravation, they'll break too. Get a nice one. Anyhow, I'm gonna just move this and this point labeling here. And attempt to draw a circle as nicely as I can. Right. Imagine you have a circle like that, right? Not as ugly, right? But that describes with a picture what is written here verbally, right? If the distance d square root of 41 is a diameter, which would make this go through the center, write the equation of the circle, right? If that is the case, if those are the conditions, right, we would need midpoint, right, because that is the center of the circle, otherwise known as h comma k, right, an x and a y respectively, and we need a radius. Right, because that's how the formula is written, right? This is a situation where, again, you got to be careful with the labeling in English. All right, English gets you in trouble a lot when you're teaching math, especially, and as a student, of course. All right, so what's the formula? All right, well, the formula in standard form is this: r squared is equal to x minus h squared plus, maybe I should scoot this over a little bit, y minus k squared. Okay. Hopefully that's good to superimpose, right? We already calculated the midpoint, right? In this case, the midpoint was negative a half, comma 1. So you can go ahead and put that in place of h and k immediately, right? In this case, because you're not dealing with 2 points, you're just dealing with the midpoint. All right? Don't go to sleep, please. I'm not that boring. All right? You're going to leave the x here and the y behind. All right? Just be careful. Again, there happens to be minuses in the formula. So if there's a negative in your midpoint, and there would be in this case, you're going to have to incorporate that. All right? And then over here, this happens to be written as 1, just substitute a 1 there. All right? Just fix it, you know. What would end up happening is that this would be x plus a half squared plus y minus 1 squared. All right. Now, insofar as the r value is concerned, all right, this is a genuine radius, but we have a diameter in this case. So we have to remind ourselves of something. A couple of points to keep, all right? A radius is equal to a diameter divided by 2. So 2 underneath it. Right? At the same time, if it were from the perspective of a diameter would be 2 radii. Okay? So we want a radius in this particular case to substitute here. All right? So we're going to have to take the figure that we have, square root of 41, and then appropriately divided by 2. Right? So over here, right, if our diameter is in fact a square root of 41, you would put a 41 in place of a diameter. And then remind yourself that it's over 2. Right? That means that this already is a radius, even though that's not a very satisfying figure, right? It is technically simplified in the ratio style of writing it. So you would put square root of 41 over 2, all right? And this is still technically squared, all right? Because that is a genuine radius as it is. Now, if you want an actual satisfying figure, remember that square root of 41 is almost 6.5, right? 6.4 is what it's rounded to. It's at the 10th place. All right, half of that would be the radius, so it's 3.2, you know, if you want a decimal. Anyhow, if you leave it like this, all right, it is correct, all right? That, in theory, should be the equation of a circle in standard form, all right? If you want to get rid of the radical, all right, just remember something. You have to be very consistent, all right? The square here doesn't just affect the top thing, it also would affect the bottom thing, right? If the value here is actually 3.2 approximately squared, that's the radius as a figure, a decimal figure, all right? Then when you square this, you should still have that same decimal equivalent, all right? When you square radical, all right, essentially you get 41. It exposes the guts, the radicand. All right, if simultaneously you're squaring the 2, all right, what you end up here with is 41 over 4. All right, so you could in theory write this like this: x plus a half squared plus y minus 1 squared. Okay. I think probably because this is not going that far, and the fraction or the ratio would be better to say, is technically simplified as it's written this way. This would be more accurate to standard form. Right? I think this, I personally prefer a decimal, but hey, that's just me. All right. Now you might wonder, well, wouldn't you get 10 point something if you simplified 41 over 4? Yeah, but unfortunately that would be the radius already squared. What you would have to do if you wanted to get the decimal at that point using these figures is take the square root of that. All right. The square root of 10.25, as that would be 3.2 again. Right. Anyhow, so this would be the preferred way to write it, as you see here, circled. All right. Now, one more of these and then I'll stop. What would happen if d, which equals square root of 41, this is a distance, d, right, were a radius instead? Right. And you were then asked to write the equation of a circle. Starting with a fresh piece of paper, all right, in standard form, just to be a good guy, all right, in standard. I'm going to put those points back, 1, 2, 3, down 1, over 2, up 3. In this case, what's being described here is a much larger circle, and in theory there's two possibilities, right, if they don't give you any more specific information. So I'm going to connect these, right? This is a distance, right, at this point between 2 points. But what if it is also a radius? Well, there's 2 points here, right? In theory, there could be a much larger circle, larger than the one that was here before. It basically looks like that, right? Where that is the center instead, right, of the midpoint that we calculated. So you'd see something that looks like this, right? And in that event, this would be a radius instead, right? But in theory, because it's not specified, what if that were the center instead, right? And this is still a radius technically. Then you have a circle that would go something like that. Right? That means you're going to get two different formulas, right, that are the equation of a circle in standard form, right? Even if they use some of the same parts, they may be using, they're going to use the radius, all right, but they'll have different midpoints, different centers, right? This is supposed to be a center, it's just a very badly drawn circle. That doesn't really help. Okay. All right, this is a center. All right, and now this would be a center. So hypothetically, if the center in this case is this point, -3, -1, and if the center of the circle in this case is 2, 3, all right, and the R value is equal to the square root of 41, we're going to get 2 different equations. Okay, Here is the formula in standard form. R squared is equal to x minus h squared plus y minus k squared, just to have it. R squared is equal to x minus h squared plus y minus k squared. Right. Just be careful as you're inserting any things with signs. The center here would go double negative for the 3 and double negative for the k. In this case, you don't have to worry, it's just straightforward. Right, so you have 2 and 3. Right. In place of the r, sometimes it's good to draw a little parentheses, like a little pocket that you're going to fill around the letter. All right, just drop this in here, square root of 41. All right, and square root of 41. If I were less of a ding-dong, I would have probably been consistently using the same colors here, so blue, sorry. And there you have it. All right. Clean it up for presentation purposes. So you could leave it as the square root of 41, technically, but my instinct is to simplify it down to just 41. And then you have x plus 3 squared plus y plus 1 squared for the blue circle. That would in theory be happening here. And 41 is equal to x minus 2 squared plus y minus 3 squared, right, for the red circle. Okay. All right. And that's it. All right. Let me turn off my projector, just spare the bulb here, and I'll just tell you what the plan is. Okay. Some light in here. All right. Insofar as my open math is concerned, I think I got it to work. But before I give you a formal assignment, I'm going to have you do an intro assignment. There is only one thing that should be available to you as of the moment of my recording this in Canvas. It seems to be that you don't need to go to the My Open Math website. So, all right, for homework, all right, for now, all right, try intro to My Open Math. It's just basically like a quiz. This is like a quiz, all right, in Canvas, to get you acclimated to inputting things. It's a little, this particular software, I mean, it's nice in theory because it's free, but it's kind of finicky how it likes you to enter information. So this is a good use of our time to get acclimated to using it. I just want you to try to do that right now, all right? What will happen eventually, all right, soon, all right, I'm gonna have you try, probably practice 2.1, all right, for actual credit, all right? I didn't set a date on it, and it's not available to you yet. All right, because again, I want to see if this works before I give you that. All right, but that's the plan, long term. All right, when this becomes available, it's not going to be due immediately, but I would try to do it immediately. You'll have some time. I haven't decided, how long yet, but you'll have a sufficient amount of time to work on that. All right, and that's the thing that you'll get an actual grade for. It should show up in Canvas, in theory, in your grade book. All right, but please humor me. Try this, all right, because you want to get used to it, and I want to see if it actually does work, all right, because right now it's kind of untested. Okay, all right, I'll give you some written instruction, not just to talk at you when I post this. Okay, thank you guys for listening. All right, I will see you again on Wednesday. All right, so tomorrow. it's technically 2 days from now because it's still Monday, but on Wednesday's class, there'll be section 2.2 coming, all right? All right, thank you. Be careful out there.